When a magnetic field and an electric conductor is in relative motion, a current flow is created in the conductor. This is what induction is in physics. But in math, it's a completely different story. Mathematical induction is a useful technique to prove mathematical statements. There's little drawback to this technique though. It can only be used to prove statements for natural numbers. That means the whole numbers are integers greater than 0, like 1, 2, 3, 4, and so on. Nonetheless, it's a quite useful tool. Let's take a look at these two mathematical statements here. The first one states that for all natural numbers n, the sum of 1 through n can be written as n multiplied by n plus 1 divided by 2. And the second statement necessarily means that if a natural number n is greater than 3, then the factorial of n is always greater than 2 raised to the power of n. Now, the approaches required to prove these statements are very different from each other. Fortunately, using induction, we can easily prove both of them. To prove a statement using induction, we need to follow 3 steps. Checking the base case, assuming that the statement is true for n, and proving the statement for n plus 1. Let's take a look at what these steps mean. The first statement is true for all natural numbers, so the base case will be the first natural number, which is 1. Let's check if the statement holds for 1. On the left side, it will be the sum of all the natural numbers from 1 to, 1. And on the right side, it will be 1 multiplied by 1 plus 1 divided by 2, which equals to 1. So, the statement holds for the base case. Now, let's assume that our statement is true for n. That necessarily means that we assume that the sum of 1 to n equals to n multiplied by n plus 1 divided by 2 is true. Now using this assumption, we need to prove that the statement also holds for n plus 1, which is the third step of proof using induction. Now, what exactly do we need to prove? The sum of 1 to n plus 1, according to our statement, should be n plus 1 multiplied by n plus 1 plus 1 divided by 2, which equals to n plus 1 multiplied by n plus 2 divided by 2. Adding n plus 1 to both sides of the assumed statement, on the left side we have the sum of all natural numbers from 1 to n plus 1. And on the right side we have n plus 1 plus n times n plus 1 divided by 2, which after simplifying becomes n plus 1 times n plus 2 divided by 2. This is exactly what we expected, so it completes our proof. We just proved that the first statement is true for all natural numbers. But how does this proving method work? Let's find out. Proving a statement using induction is analogous to the domino effect. In a set of vertically placed dominoes, if we know that the first domino will fall and that for all dominoes, the next domino will fall, we can be sure that all the dominoes will fall. Induction works exactly like this. The base case is like the first domino. The second and third step, which is proving that for all n plus 1 is true, is similar to making sure that all the dominoes push off their neighbors. For example, in the first statement, the base case 1 is true, and for all n plus 1 is true. That means the whole statement is true. Suppose, if we take n equals 1, then we know that n plus 1 for 2 is true. Since now we know that the statement holds for 2, let's take n equals 2. Now we know that the statement is also true for 3. And it goes on like this forever, necessarily proving our statement. now know that the sum of all the natural numbers from 1 to n is n times n plus 1 divided by 2. It works for any natural number no matter the size. But what is the sum of all the natural numbers starting from 1 all the way up to infinity? It should be this, right? Actually no. Surprisingly, the sum will be minus 1 by 12. How? That's a topic for another video. Now that you know what induction is and how it works, let's take a look at the proof of the second statement. The statement holds for all natural numbers greater than 3. So, the base case is the first natural number greater than 3, which is 4. Now, we can easily check that the statement holds for 4. Let's assume that the statement is true for n. To complete our proof, we need to prove that the factorial of n plus 1 is greater than 2 raised to the power of n plus 1. To do that, let's multiply n plus 1 to both sides of our assumed statement. On the left side, we have the factorial of n plus 1, but on the right side, things don't look much friendly. Fortunately, we can sort this out. In this proof, n is greater than 3. Let's add 1 on both sides, then we get n plus 1 is greater than 4. Here, we can see that 2 to the power n times n plus 1 is greater than 2 times 2 to the power n plus 1, which is of course greater than 2 to the power n plus 1. Now we have what we were trying to find, and that completes our proof. So this is what mathematical induction is. To be precise, weak mathematical induction. There is another type called the strong induction. The only difference between them is in step 2. In case of strong induction, instead of assuming that the statement is true for just n, we assume that the statement holds for all the natural numbers starting from the base case all the way up to n. Although the names suggest otherwise, both types of induction are equally viable in mathematical proofs. So this brings us to the end of this video. Hope you guys enjoyed it, and if you have learned something new from this channel, please let me know in the comments. And of course, have a good day.